believe this is number 5 on AP Prep number 6. This is the area and volume BC version. And anyway, not a lot of BC stuff going on here, though. It's a pretty typical area and volume question. They give us y equals 20 over 1 plus x squared. They want us to find the area between that and the line y equals 2. And then they like the volume when that region is rotated around the x-axis. So let's look at those two parts. I've made a sketch of this. The function kind of goes up like that, goes down. Remember when you find an area, you're really finding areas of rectangles. And so you're really just coming in here and saying, I can put a rectangle in here. You need a point that links to your function, like x comma y. And then down here, you know the y coordinate is 2. So your dA statement, to find the area of one of those rectangles, it's the length times the width, you're taking the y value, upper value minus the lower value to find the height. So maybe we want to call that like a y2, something like that. So the length is going to be y2 minus 2. The width there, you can see, is a little horizontal change. That's going to be a dx. Okay, so we need to write this all in terms of x. That's going to end up being the integral. The y2 function, or the y function, is just the 20 over 1 plus x squared minus 2. This whole thing times dx. And the intersection points are, I believe, at -3 and +3. And so that's what our integral would end up looking like. So let's go see here if that's the correct answer before we move on. Yes. Okay, we're good to go there. Part 2 asks us to find the volume if this is rotated around the x-axis. So it's not the best drawing in the world, but we'll live with it. So you want to show one of your disks. This is a disk method problem. And so one of our disks might look something kind of like this. And then you got to be careful because you've got this region above the x-axis, so there's going to be a space below the x-axis as well. And that's basically your cutout of your disk. And then that disk has just a little bit of width. Okay, so it might look something kind of like that, all right? So this is a washer method problem. I prefer to view this as basically taking an outer volume minus an inner volume. So I view this as the integral of pi big R squared h minus the integral of pi little r squared h. A lot of times they'll turn this in one integral at the end, but something kind of like this. So you just have to write your radii in terms of the function. So let's look at our big radius here. You've got this big radius that's going up here. That's the point x comma y. Notice the radius is going from y down to 0. So the whole radius there is actually y. The height of one of those disks is a dx, so we need to write this all in terms of x, all right? And then for our cutout, our inner, so we have basically an outer volume minus an inner volume is really what's happening here. That inner disk, notice the radius is coming back here. That radius is always going to be 2, okay? So you could say it's 2 minus 0, but anyway, the radius is always 2, and of course the height of the cutout is still a dx. So we can take the integral, still starting at -3, ending at +3. This is all in terms of x, and we're going to have pi, which I'm going to factor out. We have our radius, which is our y equation, which is that 20 over 1 plus x squared equation. Now be careful, it's the radius squared times dx minus the integral. Again, I'll factor out the pi. You have 2 squared times dx, or 4 dx there. And you could make this into one integral if you wanted to. You could factor out the pi, do -3 to 3 of 20 over 1 plus x squared minus 2 squared. And this whole thing times dx. So you've got your outer circle area minus your inner circle area, and then you're multiplying that whole area of the ring basically by the width. But I just prefer to write it this way, and for an FRQ that's fine, but multiple choice they might reformat it to look like that. Let's look at their answer here. Let's see what's going on. Looking good there as well. Okay, part C. It says in part C, the region of R is the base of a solid. The cross sections perpendicular to the x-axis are semicircles. And we want to find the volume of that solid. All right. So they love these cross sections. There's some kind of weird shape. So I'm going to start out here by just kind of drawing my basic shape. Again, it's going to look something kind of like that. Okay. My cross sections cut perpendicular to the axis are half circles. So they're basically they're going to look like this sort of thing. They're kind of coming up like that. And then remember, your half circles will have just a little bit of width here. So they might look something kind of like that. Okay, it can be a little bit hard to draw these sometimes. Maybe it's easier to do like that. But anyway, that's what your slices look like. So you can write a dV statement. The volume, normally it would be pi r squared h for a full disk. This is a half disk, so it's going to be 1/2 pi r squared h. Now be careful, the radius is not that full length. It's only half that length there. Okay, so when you write the radius, you can pick a point on your curve. That's the point x comma y. The radius is not y. The radius is 1/2 y. Okay, and that radius is being squared. Okay, and then the height, you can see there, this is, well, if this was projecting out vertically at us, that height would be a little horizontal change, and the height would be a dx. And so everything needs to be written in terms of x. So let's put all this together. Once again, we're adding these up from -3 to +3. I'm going to factor out the pi. We've got the 1/2. We have 1/2 the y value squared, okay? The y value is 20 over 1 plus x squared. So again, the radius is half of y. So this whole thing here, half of y, would be our radius. The radius is being squared, okay? And then we're taking half of that, so there's another 1/2 out in front. And then you've got a dx, and you're taking the integral of that whole thing. All right, let's go look at the answer on this one, see if that one also works. So we've got the, oh, what did they do here? Okay, I like their top line better. So they've got the, I made a mistake. This isn't the x-axis. This is the point x comma 2. Y minus 2 is the radius. So it's going to be 1/2 y minus 2. I'm going to have 20 over 1 plus x squared minus 2 is my radius. I'm taking half of that, okay, because half of that length is the radius. Squaring this whole thing that's the radius. And I'm taking half of that because it's a half circle, okay? And now I think if we look at it, I think that'll match up with what's going on here. Yeah, a whole lot of 1/2s. They factored that other 1/2 out, so they've got a pi over 2 out in front, but that's the same thing. That's not a tricky problem. I don't think it's impossibly difficult. It's a slight extension on what we've done in some of these square cross sections and that kind of thing. But you just got to be very careful. A lot of 1/2s in there, and I was kind of lazy and lost that -2 as well because I didn't draw the whole graph. So got to be careful with that.